Hi, good evening, and welcome to the ZP webinar. So we like to do this webinar once a week, and it's really just about answering technical questions that have come in during the week. So I will jump straight into it and say, even though it says the 19th of May here, it's actually the 18th of May. We've just gone a little bit early, rather do it in the evening rather than do it tomorrow morning. So we'll just go quickly into it and say that we're primarily answering 4 questions this evening. One of them is somebody's already a user of a ZP screen printed electrodes. I think they're having a few problems and they're kind of asking questions about going over to a parallel electrode in order to help them with capacitance measurements. But I really want to make the point that actually those ZP electrodes are really repeatable. Once you start going away from them, you're entering a whole world of sort of irreproducibility in the science. And I also want to emphasize that actually we do use them in EIS, electrochemical impedance spectroscopy types measurements, both resistance, if you want to use that, and capacitance, and I will make a big point of that during the webinar today. But be super careful about, if something's not quite working in the lab, it's not always the screen printed electrodes, and you might have to kind of share data with us, share well annotated slides with us, because at ZP we really are able to help. Something that happens a lot, I'm also very interested in people using our gold electrodes maybe in immunoassays. I would also say that if you are working in immunoassays, strongly think about using carbon electrodes as well. You can, people talk about the pros and cons of gold versus carbon, but there's one thing about gold is it's 28,000 times more expensive to purchase than carbon. And in the end, everyone is looking for a low cost biosensor, is what it comes down to, especially if you're doing immunoassays. It's just a simple fact. You cannot, these days, you cannot make low cost gold based sensors. Please, it has to go over to carbon. But I'll talk about making immunoassays on top of gold electrodes anyway, with a special personal plea. Please transfer over to carbon. It can be done. I'm also going to help with the troubleshooting of a glucose sensor and also the single purpose biosensor circuit. So there's a company that has some technologies from us, including test solutions, electronics in the form of the single purpose biosensor circuit, and also some glucose sensors as well. And they were having problems, but they were very good. They did send me a slide well annotated. I could immediately see what was going on. And then I was also then, because they were able to help me so well, I was then able to help them, because actually we went in the lab and did exactly what they were trying to do, and we just did it first off as well. It's also useful as well because actually when we ship people things like the electronic board, we actually had an outgoing quality check on that board to make sure that it actually passed, and it did actually pass our remits, let's say. So we were confident in it. I just want to say though that we don't give out those quality data to the clients, because if you want to be part of our quality system, then you have to be formally engaged with us through a proper program, etc. But we did actually have a look at the quality data going out as well. Question number 4 is about calibration or testing a nitric oxide sensor, hydroperoxide sensor, and oxidation reduction potential type sensors. And I will make a comment on that at the end. We do have 3 upcoming webinars. There's a couple of webinars next week. One of them is on commercializing biosensors. So if you're interested in what I would call IVD, in vitro diagnostics, this webinar will be definitely useful to you. We always do 2 webinars each on the day, one in the morning, one in the afternoon, because we want to be as geographically inclusive as possible. And the nice thing about being based near London, UK is it's kind of one of the best time zones, because we can overlap with people in Asia through the morning webinar, and we can overlap with people in the Americas in the afternoon session. So that's why we hold 2 sessions on the day. If you see a link, if you see any URLs or links pop up, don't worry, I will post them underneath the webinar, underneath this video rather as well. If you're interested in wearables, we do have a wearables webinar on the 19th of June. Same format, one in the morning, one in the afternoon. Particularly, this might be super interesting to people who have more of a sort of academic inclination. We are having a webinar next week, really trying to highlight technologies for academics rather as well, on the 21st of May, which is about 3 days from now. Again, all links will be put underneath the video afterwards. Question number 1 really is, we have a user. I love to have users. They are using our screen printed electrodes. They're having some problems with a capacitance measurement, and honestly, I'm worried when people immediately think, oh, it must be the electrodes, and it's not necessarily. But they have come to us and said we were thinking about changing over to something like this. I mean, and I just want to say that as ZP, we haven't come to these electrodes by accident. You know, when you look at an interdigitated electrode like that with parallel electrodes, ZP's done these kind of electrodes. This spiral might look very different from the interdigitated electrode, but this is one of the first, let's say, electrodes we made 10 years ago now, you know, a long time ago. But we actually stopped doing that kind of thing because actually what we found out was when we were trying to do impedance type measurements, you know, by impedance I'm thinking about the real and imaginary planes, which is resistance, capacitance. We just found it didn't matter what geometry we ended up using, whether it was this kind of rectangular electrode geometry or spiral geometry, or in fact we even took a kind of classical two platinum parallel electrodes facing one another. We got the same results. I want to say something about electrochemical biosensing. This whole thing that the geometry really, you know, within reason, the geometries actually are not so important to the signal. So when you think, oh, I'm going to fix all my problems by just going to this new geometry, really sorry, it's not. And I do want to sing the benefits now of the ZP screen printed carbon electrodes. I am super biased. If you want to make, now I'm going to show you two sets of data here. One of them is going to be differential pulse photometry and one of them is going to be EIS data. But if you want to make a capacitance type measurement on a ZP electrode, they really work well. We do this a lot. Now here I'm going to be using differential pulse photometry, but if you see, for me, impedance spectroscopy, square wave voltammetry and differential pulse photometry, they're quite interchangeable for me. If it works well with DPV, it will work well with square wave and EIS. If it works well with EIS, and square wave and differential pulse will also work quite well as well. Now I bring that up because we are definitely making capacitance and resistance type measurements on our screen printed electrodes, and we're doing a really good job of it. Here I'm using a carbon electrode. We're using pyrene NHS, which is a very reactive molecule. The NHS group reacts with the antibody. We're blocking the surface for non-specific binding with chitosan, and we measure the we're measuring the way that we're actually functionalizing this using cyclovoltammetry. And then we actually do some testing, and we got really good. And we are doing what's here called Faradaic testing. And that was one of the things is, if I'm going to do a capacitance measurement, either using the resistance element, which you sometimes call charge transfer resistance, or the capacitance element, which is sometimes called double layer capacitance, I would actually do Faradaic impedance spectroscopy. Faradaic impedance spectroscopy means you've got some sort of redox molecule in the solution that wants to undergo an electrochemical reaction, but actually that electrochemical reaction is interfered with by the change in the surface when you get binding. So for example, you know, we may use ferrocyanide that otherwise wants to oxidize. In fact, in this case, it may even be ferricyanide that wants to be reduced. But in binding, there's a change in the surface and the signal changes accordingly. So I suppose when people say to me, oh, well, do you have any parallel electrodes? We're having problems. Tell me the problems. Give me some slides. Give me annotated slides, and I actually may be able to genuinely help people. Which you'll see now that somebody gave me some slides. I immediately saw what they were doing, and we were able to actually do the experiment they needed to do, but we were able to do it in our lab. So be careful about just sort of pinning some problems you may be having on the electrodes that you have, especially if the electrodes come from ZP, because we're really, I mean, we do a lot of work on these screen printed electrodes. We are not just, when you're buying them from ZP, I say this all the time, but we are using these electrodes a lot. They are the best. They have to be the best because we need to be doing some good work for our really large clients. And so there's something very strange about the ZP business model. Biggest user of ZP screen printed electrodes? ZP. It's the only company in the market that's like that. And also, you know, we are able to use the capacitance elements on our screen printed electrodes. We do it a lot. These are low concentrations of proteins being detected using EIS, electrochemical impedance spectroscopy. The capacitance signal is kind of at the, I don't know if it's the zenith is the correct term here, but at the tops of these semicircles, there's a very capacitive element up here, and we are able to use that to measure on our screen printed electrodes. So be super careful before you think that maybe the problem is a screen printed electrode. If they're from ZP, it definitely is not. And I just want to say that one of the problems about going away from ZP's electrode with some of these parallel type electrodes is you'll know it. And if you come to our webinars next week, there's no calibration going on when ZP is often doing our work. It's because we spend so much time making sure that those electrodes are repeatable and of good quality. Again, because ZP is the one that uses these electrodes a lot. So it's a dangerous thing to actually go away from this platform then, because you're in the world of R&D, let's say screen printing now. And the ZP, we're one of the few companies that actually, when we're screen printed electrodes, we're doing it because we generally have medical type products being developed and manufactured on top of these screen printed electrodes. And we make a small subset of what we're manufacturing available to the R&D community. It's a very different mindset. So when you see you can see the repeatability of our work in things like, you know, even though you're maybe interested in capacitance as the signal, capacitance is really just it's just part of the, let's say, one side of the coin when you're making electrochemical measurements. You know, the thing I'm trying to emphasize here is that the signal, and it's a voltammetric signal, is, and these are three, every time you see in each color or each concentration there's three signals. Those are three different electrodes. Please understand the repeatability of our screen printed electrodes. Otherwise, once you go away from the platform, you're back into the world of really other screen printed electrodes, which have a lot of variability. I was at a conference this week in Spain talking to people, and I said, what's the biggest problem you've got with screen printed electrodes? And it's repeatability. But at ZP, actually, we've really solved that problem, that actually we make really repeatable electrodes, and that's why you'll see us do lots of work online in our webinars where there's no calibration. Why? Because the underlying electrodes are really reproducible. So be careful when you're kind of trying to break away from this platform, because actually it's a really robust platform. We put a lot of care and love into actually these electrodes. Question number 2, if you're making gold screen printed electrodes, if you want to use gold screen printed electrodes to make immunotype assays, fantastic. My only problem with gold is, I said it 5 minutes ago, it costs 28,000 times more than carbon. 28,000 times more than carbon means that it's just not compatible with low cost. And as we go into, like, you know, these kind of global economic cycles where we may be in a slight downturn in the global economic cycle, people want to go and buy gold as a sort of de-risking of investment. So gold's actually going to, you know, it's not, gold is becoming sort of more expensive at the moment. So be really careful about building immunoassays on top of gold. With that said, we do build immunoassays on top of gold. Sometimes the science has gone so far on gold that it's too much effort to roll it back to carbon. So we do a lot of contract development, contract manufacturing, and by the time the sensors come to us, they might already be on gold, and you know, gold it is. But we do a lot of this kind of EDC, LHS type coupling, and putting antibodies onto surfaces and then blocking the surfaces to stop sort of non-specific binding. Maybe using this an excess and mercaptan hexanoic acid to stop other molecules binding to the surface afterwards. And we do have these gold, and I'm going to put those links underneath the video as well. So even though I just had a little slight sort of comment look, you know, but I do want to say it again. If you can avoid gold, please avoid gold. You will find that there's plenty of sensors on ZP's website for less than €1 each when they're made of carbon. But unfortunately, you'll find that our gold electrodes are like €7, €8 each. And it's not a greed thing. It's because gold is 28,000 times more than carbon. You can look it up on the commodities indexes. Gold is expensive. But that said, if you do want a good quality gold that's got a very good repeatability, then please do consider the ZP gold electrodes. These Nyquist plots, which come from Immunoassay, just perfect. Each color represents these 3 concentrations, and you can just see the sort of tightness in the data or the relatively small relative standard deviation. So gold it is. Now we use these webinars to support clients. So we do have a client, and this client has really done me a great favor because they are testing glucose sensors from ZP, and they're testing them on this single purpose biosensor circuit. There will be a link to the single purpose biosensor circuit shortly, but these people, you know, they sent me a well annotated, you know, slide. There's nothing worse than people asking us questions where it's just an email or an email and just a spreadsheet of data. But no, you know, here they've plotted it all out. They've explained it, you know, what they're doing. You know, they're adding 2 millimolar, then they're probably adding 4 millimolar, then they're taking off the 4 millimolar and putting on 6 millimolar, and then they're putting on 8, then they're putting on 10. I appreciate they're taking off the solution each time. You can see it in the data, the way it drops down, but that's completely fine. I mean, we do this kind of work all the time. The only problem we've got here is they are not getting the steps that we would otherwise expect. But I think I said at the beginning, the nice thing is that, you know, when we know who the company is, we can actually see, you know, the shipping details, what we shipped. We were able to check the quality records on the electronics, you know, and make sure that we pass the quality control. And we also then went into the lab, and I said, look guys, we just have to make sure, you know, we did it this week, by the way, when we found out there's a problem. Then they gave us a well annotated slide. That then gives me enough evidence to say, okay, so we saw what they were trying to do, and we went into our lab and actually did the same experiment, except we were able to show that we were able to get these increases in glucose. It wasn't the best data we've ever got, but I just wanted to kind of quickly go in there and sort of say, hang on, can we get glucose signal out of this glucose sensor and this board working in conjunction? And the quick answer is, unfortunately, we could. So it doesn't help the client too much, but what it does answer to the client is whatever is happening at their site is happening at their site, and it's not intrinsic to the system itself, because I got our guys to just check again this week. You know, and it costs, as you can appreciate, you know, you pay the salaries, we have to have the meeting, the data had to come here, I had to prepare the slides, you know, so these things, you know, you can appreciate that, you know, we do. But, you know, when there's a problem, ZP goes and makes sure that, you know, we try to figure out, you know, at least, you know, is the system working, let's say. So I'll wait to hear back from them. Now, question number 4, somebody wants to calibrate or test nitric oxide sensors, hydroperoxide sensors, and oxidation reduction potential sensors. The nitric oxide and the hydroperoxide sensors are amperometric, and the oxidation reduction potential, it's got the word potential in there, is a potentiometric sensor. Let me go forward fairly fast and say, the way we generally, one way that we like to calibrate sensors is we'll kind of have our sensor that's been functionalized with for either NO or hydroperoxide or ORP. We may put them in a beaker like this. This is one way we do. And we'll have the sensor kind of turned up like that. And in fact, you can see Andre here, he's working with us exactly in that configuration. He's got the sort of sensor on top of a magnetic stirrer, stirring away, and he'll be taking aliquots of material and adding it to the sensor. And every time he adds in an aliquot of material, the signal jumps up. So this is the first time he adds solution. Then he adds a bit more of an aliquot of a test solution, and the signal goes up a bit more, and the concentration rather goes up a bit more, and then the signal follows it. So this is quite a fairly common way that we test or calibrate sensors. Now, the nitric oxide is a really nitric, make sure I spell that right, is a really painful setup. I did take this image off Wikipedia. I'm hoping I'm using it simply in the purpose of education. And, you know, for example, the material I'm about to give here is freely given. You've got to be very careful with nitric oxide. It's really much more toxic than maybe people otherwise think of it. I mean, NO, nitric oxide, is a big signaling molecule, obviously, in biology, including human biology. Therefore, it's not that surprising that it's really toxic. So unless you're a chemist, you've got a fume hood, you've got personal protection equipment, you've done a safety assessment on this, do not attempt this. This should not be, well, just simply do not attempt this outside of I mean, I think this is, skilled laboratory workers should be doing this, and they should have done all their quality considerations on this. So the procedure I'm about to describe ends up producing you a solution that's at about 1.8 millimolar nitric oxide concentration. So for this, you do need an extraction hood or a fume hood. You need equipment where you're able to, you're going to generate nitric oxide in a glass vessel, and nitric oxide will then come out as a brown gas, and you're going to flow that brown gas into DI water, where actually it will solubilize and or dissolve rather, and become about a saturated solution of 1.8 millimolar. So you need 100 mils of DI water. You need the following chemicals in a round bottom flask. That's iron sulfate, which you dissolve in about 20 to 30 mils of DI water. 8.5, it's a bit accurate this. This is badly written here. I'm going to slightly correct this. I can see I made a little typo here. 8.5 grams of iron sulfate in 20 mils of water. 17 grams of sodium bromide in about 20 to 30 mils of DI water. So sorry about... yeah, that's right. 4.8 grams of sodium nitrite, NaNO2, in 20 to 30 mils of DI water. And you mix those together, and then you add the remaining 100 mils. So if you use 30 mils, 30 mils, and 30 mils, that leaves 10 mils. You add the remaining 10 mils of DI water. Now you have to close this immediately because it's going to start fuming some brown gas, which is nitric oxide. It's super toxic. Be super careful with this stuff. And then you actually, it sounds ridiculous, but the brown you have to flow that brown gas into about 1 liter of DI water, and it's going to end up saturating that DI water, the deionized water, to about 1.8 millimoles. That becomes your stock solution. Nitric oxide is a real pain because it's not like glucose or lactate or ketones or hydrogen peroxide where it's actually quite stable. It's not stable. It's nitric oxide. It's going to want to come out of that solution fairly quickly. So you have to prepare it quite quickly and use it quite quickly. To run the sensor, you need to run it amperemetric mode. The voltage you're using is about 1.05 volts, quite high. And here we're just adding aliquots of that 1.8 millimolar freshly prepared solution to our test solution. We watch the signal increase accordingly. Nitric oxide is a pain to generate. It's toxic. It's an important marker in biology. We get it. But it is no fun. I've done lots of projects on nitric oxide. It's just no fun to deal with. But once you prepare that 1.8 millimolar of stock solution, it's not going to be stable for that long. So you have to actually start using it to test the sensor that way, in this kind of beaker configuration where you start off with 0, you add an aliquot, whoops a daisy, you add an aliquot and you bring it up to like 9 micromolar, 18 micromolar, 27. So we can see we're just adding the same volume in order to get it up high. Hydrogen peroxide is a bit easier. Hydrogen peroxide here, we've got a sensor, it's amperemetric. We're testing at 650 millivolts. We add in 0.5, 2, 4, and 10. Steps up really beautifully. Hydrogen peroxide is much easier to deal with. Again, you can do it in this kind of beaker kind of configuration. And I actually had a link to a, in fact, I've got a test solution online here. So I got a link here that you can find the test solution online as well. This redox is different. Redox is a potentiometric measurement. So you're really running this in what we call open circuit potential mode. Open circuit potential mode just is, it's a really bad term. Open circuit potential just means it's a high impedance method of measuring potential. It's high impedance so you don't flow current. With these ORP sensors, these oxidation reduction potential sensors, if we give up anions, we get a delta plus. If we take on anions, we get a delta minus. So we're just measuring the ability of the solution to give or take away, let's say, charge from the electrode. Here we've tested it. We can see that we get poor resolution between 0.001 and 0.01. So we can't really resolve those two, but we can easily resolve 0.01 millimolar of, in this case, it's probably ferricyanide, 0.1 molar ferricyanide, 1 molar ferricyanide. We can see the signal. That's the plateau, that's the plateau, and that's the plateau. Again, we just go in with the sensor into the solution, and in fact we do have a calibration solution for that, but again it's adding aliquots into the beaker and watching the signal change accordingly. So question number one, I do respect that people want to change geometries, and in this case they want to go for these kind of parallel interdigitated electrodes. There are links in this webinar, and I'll put them underneath the video, where honestly we have absolutely changed geometries on screen printed electrodes, and it actually makes no difference to the signal. I think the idea of interdigitated electrodes, I can see that being interesting, things like chemi-resistors, but I don't think that these kind of geometries are as critical as people otherwise would like to think. And I have data on the website, and I'll put data underneath this video, where I use lots of geometries, admittedly in a conductance mode, and you know what? They all gave the same signal. I can think of good reasons as to why. It's things like, actually the molecules don't know about the geometry of electrodes. Our electrodes are so close to one another, actually that sort of distances and the resistance due to those distances is pretty negligible actually. So it's not, if you talk about macro electrodes that are, you know, in large electrochemical processes, you know, electrolysis where you're making kilograms of material, that's a different story, but not in this very sort of millimeter scale, micrometer scale electroanalytical science. It's not important. You can do immunoassays on gold electrodes. ZP has some really good gold electrodes. We're busy at the moment on a really large project using all these gold electrodes to make some fantastic molecular type immunoassays. But if you can avoid gold, go for carbon. You will find links underneath this video for carbon electrodes from ZP. Troubleshooting a glucose sensor. It's great these people have annotated their data so beautifully. I can see that, yeah, you're not getting a signal with the glucose concentration. It is strange, but at least you can know one thing. We saw the experiment you were trying to do. We took the equipment that you've got, your equipment, but actually you got, you know, we took the same glucose sensors that you would be using, the same electronics that you would be using. The only difference is you do it there, we do it here. And this week we were able to actually show that, you know, that experiment does work. So it's curious what's going on in your lab, but just be certain of one thing: the technology does work in our lab. This nitric oxide, what a horrible material to be using. Sorry, I was a bit tired this evening, and I tried to put together a bit of a procedure for you. But you can make nitric oxide in the lab. You bubble it into this DI water, and that gives you about a 1.8 millimolar stock solution. Then you can add aliquots to that and calibrate that way. Hydroperoxide is much easier. It's a fairly stable solution, and oxidation reduction potential. You run that in open circuit potential mode, and I have linked to a calibration solution that you can use there. And I wanted to say thank you. So thank you so much for if you're watching live. Thank you so much if you're watching the recording later on. Thank you so much if you are actually using ZP technology. If you've got any questions on ZP, we do answer them. You can see that this web, you know, that it's not just about getting materials and stuff from ZP. Actually, we will look at people's data, you know, and go into our own labs and test things. Or somebody wants to know how to make nitric oxide, I'll go and look at our own SOPs and actually find out how to do it, you know, for example. Or somebody's trying to make an immunoassay, and I'll show you our own immunoassay data and how it kind of works. So you can see at ZP, it's not just about the products and the technology, it's also the fact that you can almost have this kind of real-time Q&A with ZP as well. So don't hesitate to reach out to us if you've got any questions. Otherwise, have a good rest of the weekend. Okay, take care. Have a good one.